Click the bell icon to get latest videos from Ekeeda.
Hello friends, today in this particular video series we are forming one video which is related with the prerequisite of the subject, and the subject we are doing is EDC, that is Electronic Devices and Circuit 1, and Analog Electronics. Both are from Electronics and Telecommunication Engineering branch and Instrumentation Engineering branch combinedly. So first of all, what we will do the complete common subjects, common topic, common subtopics, all the common concepts that are under EDC 1 and Analog Electronics, and then in the second part we will complete the EDC 1 which is not in the common part, and then we will complete the Analog Electronics which is not under EDC 1. Okay, so let us start with the prerequisite of this particular chapter, that is called as diode circuit. Let us come to the point. As far as prerequisite is concerned, we have to know that BEE subject, that is Basics of Electronics and Electrical Engineering. In that we all have learned the small concepts related with the circuit, related with the resistances, related with the AC and DC sources. So all these are nothing but the prerequisite for this particular subject as far as EDC 1 and AE is concerned. So we will learn little bit of that prerequisite, brush up all the prerequisite, and then we'll come to the point of actual subject of actual topic, that is called as diode circuit. So as far as prerequisite is concerned, first of all we should know that what is exactly AC and DC sources. AC and DC sources. AC, obviously it's nothing but the alternating current. DC is nothing but the direct current. So whenever I am talking about AC current, your symbol is this. So whether that is of voltage, whether that is of current, your symbol should be like this. Whenever I'm forming DC voltage, then it will be like this. Whenever I'm forming DC current, then it will be like this. Okay, so as far as symbols are concerned for AC and DC sources, this picture is very clear now. Okay, let us proceed further for the next part, that is nothing but the resistances. Resistance is denoted by R. Capacitance is denoted by C, and inductance is denoted by L. All these RLC circuit that we have learned in second module of BEE, we will not come to the point, that particular point again and again. Just note that whenever I am forming a resistor, capacitor and inductor combinedly, then it will be under AC circuit. When I am doing only with the resistances, then it will be under the DC circuits. Okay, so this all about the AC-DC sources and the resistances. Now we will learn a little bit about the semiconductor. So before joining to the semiconductor part, because the semiconductor is nothing but the heart of complete electronics, so we will learn semiconductor. Before learning this semiconductor, we'll just have to brush up all the energy band diagrams. So as far as energy band diagram is concerned, this energy band diagram we are relating with the three types of material. One is metal, another is insulator, and another third one is semiconductor. So as far as material is concerned, this material is divided into three parts. One is metal. Let's take an example, that is aluminium. Okay, then semiconductor. Example, silicon, and another is insulator. Example, phosphorus. As far as energy band diagram is concerned, let us consider the energy band diagram for metal, semiconductor and insulator. We all know about the valence band, we all know about the conduction band. This is all about the valence band and conduction band for metal. valence band and conduction band is overlapped. So there is no energy gap between valence band and conduction band. Energy gap is denoted by Eg. Okay. About insulator, let's come to the point of insulator first, then we'll jump into the semiconductor. As far as insulator requires large energy gap. So whenever I want to form the conduction, this is C, I'm sorry, and this is EV. EV is nothing but the valence energy level, and EC is nothing but the conduction energy level. The energy required for the electrons to move from valence band to conduction band is called as energy gap, and this energy gap is in the range of 9 electron volts. 9 electron volts is nothing but the energy required for the electrons in the insulator to move from valence to conduction band. But before that, your melting point of the insulator reaches, and that's why insulator is not a good conductor of heat and electricity. Now, what will be the remedy in between the metal advantages and insulator disadvantages? So we'll have to combine this metal and insulator and form a semiconductor, right? I'll just relate this metal, semiconductor and insulator in a different analogy. We all are living in Mumbai, so we know that if I'm talking about central local, right? So if I'm talking about fast local, that I'll relate it with metal. If I'm relate the slow local, I will relate this with insulator, right? When I will relate the semiconductor, it is in between the metal and insulator. That means I am talking about semi-fast local, right? So when it reaches from Kalyan to Thane, right? When it reaches to Thane, after that Thane, it will move fast, right? So I will relate this semiconductor as semi-fast local, right? So this metal is nothing but the fast local, this semiconductor is nothing but the semi-fast local, and this is nothing but the slow local, right? Very simple. I will draw this energy band diagram over here. Why do we require this energy band diagram? This is because, see here, this is the conduction band and this is the valence band. The difference between valence band and conduction band is very less as compared to insulator and greater than that of metal. So we required very less amount of energy to move electrons in the valence band towards the conduction band, so that my conduction process will get started. As I mentioned, after Thane, my my semi-fast local will move fastly from Thane, right? So as the electrons get this particular energy, very less amount of energy, such that electrons will move from valence band to conduction band, at that particular point conduction will get started, right? So we don't require the amount of energy which is very high in terms of insulator, and very less even at room temperature it is not possible the semiconductor to flow the electrons. So I require certain amount of energy to flow the electrons from valence band to conduction band. So unnecessarily I will not form the conduction process as it forms in a metal, right? Now we all know about metal, insulator and semiconductor. Let us throw that metal and insulator in the dustbin. Right now we will concentrate on semiconductor part. So further we will learn from the semiconductor, we'll jump to the types of semiconductor, then we'll actually jump to the diode circuit, that is p-n junction diode circuit. So this is how we will be having a flow for this particular chapter. So let us talk about the actual semiconductor. This semiconductor is divided into two types. That means, as far as classification is concerned, two major types are extrinsic semiconductor and intrinsic semiconductor. Extrinsic semiconductor is impure semiconductor. So another namakaran for that is impure semiconductor. And intrinsic is nothing but pure semiconductor. We all have learned the examples of semiconductor. Generally we use silicon, generally we use germanium. So we will take these examples only, silicon, or else we will take germanium. We have another types of semiconductor as well, but right now we will concentrate only on these two types of semiconductor, gallium arsenide and all indium arsenide, all other types of compound semiconductor as well available, but that is not related with this particular chapter. We will learn later on. As far as intrinsic semiconductor is concerned, I did give the Namakaran as pure semiconductor and extrinsic semiconductor as an impure semiconductor. So what exact difference between intrinsic semiconductor and extrinsic semiconductor? Intrinsic semiconductor में क्या होता है? I'll say that this is nothing but formed of silicon or germanium itself. No another impurity in terms of either insulator or metal. This is pure semiconductor. That's why it is called as a intrinsic semiconductor. Now you may got the difference between intrinsic and extrinsic. You can define the extrinsic semiconductor as well. Now what is the extrinsic semiconductor? Yes, extrinsic semiconductor is nothing but the semiconductor which is formed after adding the impurity material into pure semiconductor, right? So if I add any metal or non-metal, that is insulator, into the pure semiconductor crystal, then whatever I will be getting, that is nothing but extrinsic semiconductor. Now in extrinsic semiconductor, keep this in mind that दुनिया में कोई भी चीज pure नहीं रहती है, right? So even if I say this is intrinsic semiconductor, I will not get any kind of impurity. No, it is not possible. But because in दुनिया में I will not get the purity, right? So we will start with extrinsic semiconductor. This extrinsic semiconductor is again classified into two types. One is P type of semiconductor and another is N type of semiconductor. Now what is that P type and N type? Why do we give Namakaran for P type as P type and N type as N type? See this. If I am talking about simple silicon crystal, right? This is the silicon and I will be having another material such as aluminium. If I add aluminium, guys, mind well, aluminium is not having 4 electrons in its outermost orbit. It is having only 3 electrons in its outermost orbit. But silicon is having 4 electrons in its outermost orbit, right? So what that silicon is generally doing in intrinsic semiconductor is, it's nothing but forming the weak bond. That means nothing but sharing of electron. That is called as weak covalent bond. So I will form 3 covalent bond. I can form 3 covalent bond with 3 external electrons which are there in the external orbit of the aluminium atom, but where I will share the 4th silicon electron. Is it possible with the sharing of the aluminium? No, it is not possible because aluminium is having only 3 electrons. So what that silicon ka electron will do, this silicon ka electron will get sufficient amount of energy. Once it gets sufficient amount of energy, it will break the covalent bond in between the electrons and it will jump into the one of the holes of the aluminium atom. Now we will form a structure of that intrinsic and extrinsic semiconductor. Then we'll get to know that how that working is. Okay, if I'm talking about p-type semiconductor, this is called as p-type semiconductor. This is because aluminium is having one vacant space, because it is having only 3 electrons in its outermost orbit. If 3 electrons in its outermost orbit, so where that 4th electron is, so that deficiency of electron is nothing but hole, and that's why we do the Namakaran of that particular charge carrier as hole. And that hole is non-negatively charged. Non-negatively charged, we take it as a positively charged, and this positively charged hole is called as positively charged carrier, and this hole is moving on complete crystal, which is nothing but the source of conduction. And that's why for positively charged hole, which is responsible for the conduction process, and that's why this particular extrinsic type of semiconductor is called as p-type semiconductor. This p is coming from the positively charged holes, right? Now you can easily analyze that why this another type is of n type. N nothing but negative, yes, clearly. Now if we say that this is nothing but the silicon, then what kind of impurity I have to add? Whether it will be deficiency of electron or one extra electron. If I am forming n type of semiconductor, then I will have one negatively charged carrier which is responsible for the conduction process. Then I should have one extra electron which is there in the semiconductor crystal. So what I will do, I will add one impurity which is having one extra electron, and that is nothing but phosphorus. I will add one extra impurity which is having 5 electrons in its outermost orbit. So if 5 electrons in its outermost orbit, out of 5, 4 will shed with the 4 neighboring atoms of the silicon. Then where that 5th electron will go? 5th electron will be responsible for the conduction process. What it will do? This electron will acquire some sufficient amount of energy to break the covalent bond, right? And when it breaks the covalent bond, it will jump into that particular space and another electron will pop up, and in this way electron will move from one atom to another, which is nothing but the source of the conduction process. And that's why as this electron, this is nothing but the electron which is negatively charged carrier, that's why it is called as n type of semiconductor. Okay. C. Extrinsic semiconductor is impure. This is because one process that is called as addition of impurity, and that addition of impurity is called as doping process. So the process in which impure atom is added into pure semiconductor, example silicon or germanium, then whatever silicon structure gets formed, it is called as the extrinsic semiconductor, and that process is called as doping. So doping definition is so hereafter for extrinsic semiconductor, addition of impurity we will not learn with addition. We will take the technical word called as doping. Now we all know that what is extrinsic semiconductor, what is intrinsic semiconductor. Let us jump towards the joint family of p and n type of semiconductor, and that is called as p-n junction diode. Just think in that way. I have p type of extrinsic semiconductor, I have n type of extrinsic semiconductor. What I will do, I will just have this simple box of crystal which is nothing but p type of semiconductor. I have a separate box which is nothing but n type of semiconductor. Okay. Now, here we must know that characteristics of p-type semiconductor, characteristics of n-type semiconductor. First characteristic of p-type semiconductor, in p-type semiconductor, majority charge carriers are holes. Minority charge carriers are electrons. However, in n type of semiconductor, majority charge carriers are electrons and minority charge carriers are holes. In p-type semiconductor, we add impurity such as aluminum, which is also called as trivalent impurity. This aluminum is accepting one electron from another silicon structure, and that's why it is called as acceptor impurity. Whereas For n-type semiconductor, we do add phosphorus, which is having one extra electron in its outermost orbit than that of silicon outermost orbit k electrons. So that's why this phosphorus is actually donating one electron for the conduction process, and that's why it is called as donor impurity. Similarly, as acceptor trivalent impurity, this phosphorus is having 5 electron in its outermost orbit. That's why it is called as a pentavalent impurity. And when these two family gets joined together, clubbed together, one very fantastic structure gets formed that is called as p-n junction diode, provided there should be one crystalline continuity. Unless I have crystalline continuity, I cannot form the p-n junction diode. This is because there will be some noise disturbances in the junction part. So this is how we will move towards the next topic, that is actual exact topic of our syllabus, not prerequisite, that is called as p-n junction diode characteristics and working. Thank you for watching this particular video. In the next video, we will start our videos series for EDC1 and analog electronics. So stay tuned for that. Learn more and more EDC1 along with me, along with Ekeeda videos. Subscribe this channel and comment if you want. Thank you.